Welcome back, ladies and gentlemen. This is my part 2 of the tutorial that we were discussing about control systems and feedback systems. This time we will be looking at the final concepts of this tutorial, and this will be the understanding of general feedback systems and its nomenclature. And what this is to entail is to define disturbances and more extensive analysis of the block diagram. So the example I will be showing you today is as follows. It is of a telescope that is pointing at a celestial object along the Earth's polar axis of rotation, and the said telescope will then rotate via motor drive from a reduction ratio gearbox, whose bearings are, as I said, aligned with that of the Earth's polar axis of rotation. It's a bit of a wordy question, so what we have to actually do is just to pick out some fundamental points from this question. Is that, firstly, let me just quickly get this question up onto Paint, and I'll be highlighting some important sections of this question. So if you like just to pause the video and have a read of this question, up to you. Okay, so firstly, this question's asking, let's just get the highlighter up. So in order to keep a celestial object in the field of view, the optical telescope's axis of the telescope must rotate about the axis of the Earth's polar axis of rotation. So what this is entailing is you're just going to have an object around telescope that's going to be of the sorry, I'll draw a more detailed picture later on. Let's just quickly analyze this question first. So, yep, along the Earth's polar axis of rotation of a certain amount of revolutions. To achieve this is usually done with the whole telescope to be driven by a motor, a reduction ratio gearbox, and its bearings. A few more key points to analyze about this question is that it is lubricated and results in a resistance torque that is proportional to the angular velocity. Okay, that's important to note before we start jumping into this question. The other last points here we'll look at on the latest section of this question. So we're asked for, just for the telescope alone, nothing else in the system, we asked what is the overall transfer function of the telescope alone based off of fundamental theorem and mathematical derivation of the telescope's transfer function. So remember what the transfer function was. Watch my past videos as to what a transfer function is. So we require an output angular velocity, and we require it to be over an input angular velocity. So let's begin with the question. Okay. Let me just quickly put this aside, and throw Paint aside. Okay. Okay. So initially we asked transfer function of the telescope alone. So based off of that, we have to just sketch a brief image of what we would think a telescope would represent along the polar axis of the Earth's rotation. So we have the telescope, and let's say it is mounted onto a plate that is along the Earth's polar axis of rotation. Okay. Now what this entails is this object would move about the plate's motion, or the plate's rotation. So you can control this telescope via this plate here. Okay, just try to sum it down using layman's terms there. Now, firstly, we have to use a fundamental theorem of mathematics or physics to back up the derivation process. So, what we would first decide is what law would we use in order to let's just say, begin the derivation of the question. So we either use the state equilibrium equations, conservations of energies, Bernoulli's equations, conservation of mass, Archimedes principles, or heat flow rates. No, we would actually first begin with Newton's second law. So we say Newton 2, which states that the object's force is a resultant of the product of its mass and its acceleration. To put it in our example here, we're given a few hints. It's saying that there's an angular velocity, they're saying that there's a torque, so this would have to be transformed into an angular formula. That was, again, layman's terms right there. So we have to transform this into a torque is the resultant of inertia, the product of inertia and the object's angular acceleration. You notice how I denoted angular acceleration as a this is the angular acceleration denotation, and this is the angular velocity notation. However, a dash above denotes it as a derivative of said term here. So this derivative is actually dw over dt. This mathematical formula here multiplied by its angular velocity would result in angular acceleration. Okay, this is some quick backup theory there, if you've forgotten how to come up with angular acceleration. Okay, this is important to note for later on. Okay, so in our case here, because we have an equilibrium about this object, this entire object is not rotating or is not performing any unequilibrium actions. That's another layman's term right there. So we're not having this telescope falling in one direction or rotating in another, etc. It's just steady. There's nothing unbalanced about it. So therefore we would say that the sum of torques, this is the torque applied. This could be also a torque number 2 applied. The sum of torques will be the resultant of this telescope's inertia multiplied by its angular acceleration. Now, what is its inertia about? So it's not actually about the telescope's own axis of rotation, but rather the axis of rotation of Earth's polar axis. So we say point P to P. You can denote these 2 points as anything you like. So we'd say that the sum of torques about point P to P is a resultant of said terms about point P to P. Okay, that's a fundamental theorem that is backing up this question. Now let's quickly get back to the analysis of the question briefly. So we asked, the bearings are lubricated, and as a result, there's a resistant torque that is proportional to the angular velocity. So resistant torque resistant, is being applied. So there's a resistant torque pushing this, countering this torque rotation applied, and this counter torque applied, torque resistance, is actually the lubrication resistant torque applied. So that's the hint given there. So therefore we would say that there would be a dampening occurred to the rotation of this telescope. So therefore damping term for in our case is Q, as you can see in the question. They actually give it to us. Q multiplied by its angular velocity. I'm sure you've already read the question. So therefore, what is this term? How do we apply this term into this formula that we have initially derived? Well, as I said, there's the sum of torques. So you recall that this torque right here, this is the torque, sum of torques about point P to P, applied, there's a resistant torque pushing it back, dampening this initial torque input. So therefore we would say, finally, torque from point P to P is being dampened by this product, this amount, right here. This is the dampening and the resistant torque applied against initial torque point P to P. Okay, So this term would then be the result of the overall forces applied